Reasoning with a resolution principle is analogous to reasoning with other rules of inference. We start with our premises. We apply the resolution principle to those premises, apply it again to the results of those applications, and so forth until we reach our desired conclusion, or till we run out of things to do. Resolution derivation of a conclusion from a set of premises is a finite sequence of clauses terminating in the conclusion, in which each clause is either a premise or the result of applying the resolution principle to earlier elements of the sequence. Note that our definition of resolution derivation is analogous to the definition of linear proof. However, in this case, we do not use the word proof here because we are reserving that word for a slightly different concept, which we'll see a little bit later. As an example, consider a problem in the area of kinship relations. Suppose we know that Art is the parent of Bob and Bud. Suppose we know that Bob is the parent of Cal, and suppose that Bud is the parent of Co. Suppose we also know that grandparents are parents of parents. Starting with these two premises, we can use resolution to conclude that Art is the grandparent of Co. Start with our 5 premises, 4 simple clauses for the 4 facts about the parent relation P, and 1 more complex clause capturing the definition of the grandparent relation G. We start by resolving the clause on line 1 with the clause on line 5 to produce the clause on line 6. We then resolve the clause on line 3 with the result to derive the conclusion that Art is the grandparent of Cal. Okay, this is interesting, but not what we set out to prove, so we need to continue the process. We next resolve the clause on line 2 with the clause on line 5 to produce the clause on line 8. And then we resolve the clause on line 4 with this result to produce the clause on line 9, which is exactly what we set out to prove. And so we're done. One thing to notice about this derivation is that there are some useless dead ends. We first tried resolving the fact about Art and Bob before getting around to trying the fact about Art and Bud. Resolution does not eliminate all search. However, at no time did we ever have to make an arbitrary assumption or an arbitrary choice of bindings for any variables. The absence of such arbitrary choices is why resolution is so much more focused than natural deduction systems like Fitch. Another worthwhile observation about Heilbronn resolution is that, unlike Fitch, Heilbronn resolution frequently terminates even when there's no derivation of the desired result. Suppose, for example, we were interested in whether Cal is the grandparent of Art from the premises in this case. This, of course, doesn't follow from the premises. Resolution is sound, so we would never generate this result. The interesting thing is that in this case, the attempt to derive this result would eventually terminate. With the premises given, there are a few more resolutions we could do, for example, resolving the clause on line 1 with the second literal in the clause on line 5. However, having done these additional resolutions, we'd find ourselves with nothing left to do, and unlike Fitch, the process would terminate. Unfortunately, just like propositional resolution, Heilbronn resolution is not generatively complete. That means it's not possible to find resolution derivations for all clauses that are logically entailed by a set of premises clauses. For example, the clause P of A, not P of A, is always true, and so it's logically entailed by any set of premises, including the empty set of premises. Heilbronn resolution requires some premises to have any effect. Given an empty set of premises, we would not be able to derive any conclusions at all, including this valid clause. Although Heilbronn resolution is not generatively complete, problems like this one are solved by negating the goal and demonstrating the resulting set of sentences is unsatisfiable.